Okay, we start our afternoon session. The first speaker is Peter Nandori from Yeshiva University, New York, and he will be talking on flexibility of central limit theorem in smooth dynamical systems.
Thank you very much. I'd like to start with thanking the organizers for the opportunity to be here and present on this conference. It's a wonderful place, excellent community, so I'm really grateful. It's wonderful to be around, especially after this long break due to COVID. So, one of the advantages of not being around on conferences for 2 to 3 years that you don't know this is not new. So, it's not so new, but I'm telling you it's new because you don't know, right? So, I'm going to talk about everything that I'm going to talk about is joint work with these 3 people, Chang Guangdong, Dima Dolgopiat, and Adam Kanigovsky. So I will not list their names any further, but anytime I say a theorem is joint with all of them. They are all from University of Maryland. All right, so we basically have a theory which we have been working on throughout a number of papers on TT inverse transformations. That's a class of dynamical systems that people studied in the past. Is not very new idea, but we picked up on it and we derived some new properties of them. But I'm not going to list you all these kind of boring properties because you would fall asleep very quickly. Instead, I picked up some theorems that are kind of the most interesting ones, and I'm going to focus on them. So that's going to happen in the introduction, and then slowly moving towards the more complete description of results in the second section, the flexibility of statistical properties. And then finally, I give you the definition of these TT inverse transformations that is, running under the hood. As time permits, elements of proof, and final remarks. That's the plan for today. And let's get into it. So I have to start with something very basic, and that is the definition of the central limit theorem. So I'm kind of having a mindset from ergodic theory as well as from dynamical systems. So as you know very well, in ergodic theory, you have a measurable space, but you don't necessarily care about other structure like, for example, you don't necessarily have even a metric, right? You just have a measurable space. In dynamical systems approach, people usually have a metric or maybe much more like a diffeomorphism, and they don't necessarily fix measure. Maybe they look for measures, right? So when I say central limit theorem, I have to keep in mind both approaches. So I'm going to give you the definition precisely. It's not completely obvious. Okay? So central limit theorem, well, the definition that I'm going to use, right, not the only definition, is one definition that one can use, is the following, that you have a CR diffeomorphism of a Riemannian manifold, and there is an associated fixed measure. I'm not going to play around with the measure. Okay, it's like in ergodic theoretic point of view, the measure is fixed. It's going to be denoted by this funny letter, zeta? Zeta, right, yeah. All my students they don't know the Greek letters, and they somehow erased it from my mind as well. So sorry. This is zeta, okay. So you have a fixed measure zeta, which is absolutely continuous with respect to volume. And the definition of the central limit theorem is the following, that you say you have this CR diffeomorphism capital F. It satisfies the central limit theorem if there is a sequence of real numbers AR, so that for any smooth function with 0 mean, okay, so 0 in the subscript means the function integrates to 0 with respect to the only measure that I'm looking at, zeta. You have the following limit, that you take the Birkhoff sum, right? So if you sum up the function along the orbit. You rescale by this rescaling sequence, A sub n, and then you have a weak convergence to a normal distribution with 0 mean and some variance sigma squared. Now what I require here is that sigma, so this needs to hold for all sufficiently smooth functions, okay? But I do allow sigma squared to be 0, which is some case of trivial limit. What I require is that it's not always 0, so it's not identically 0. It's not 0 for all functions. There is one smooth function for which it is not 0, and I don't mind if it is 0 for many other functions. Okay, I want to argue that this is the correct definition because, oh yeah, one more remark. We say it is a classical CRT if you can choose the sequence to be square root of n, right? But it might not be, so I didn't didn't put it in the first place. So mind the quantifiers. I think I already said that if you want something weaker, like there is one function, I argue is not a good definition, because there is this abstract theorem by Burton and Denker that unless the measure is very trivial, atomic, you will always find a function that satisfies the CLT. Might not be smooth in L2, but that's kind of a very interesting result, right? So you have a rotation of the circle, you still have the central limit theorem for a very crazy function. So let's not do it. I don't want to talk about rotation of the circle. I mean, I may eventually, but it's not a diffeomorphism for which this definition holds, right? And also, on the other hand, you don't want to require too much. You don't want to require all the limits to have positive variance, because that will never happen. Just recall coboundaries. Coboundary means, you know, function subtracted by function composed with the map. That will never have a positive covariance, right? So that, I think, is a reasonable definition, okay? So that's the quantifiers that we are going to use. All right, so that's my definition of the central limit theorem. So let me try to tell you a result right away, and I'll expand on this later. That one kind of exotic example that we construct is well, I gave the definition for diffeomorphism, but I leave it to your imagination to extend it to flows. Okay, it's pretty standard. So we have a flow, an analytic flow, which satisfies the central limit theorem with this very unusual normalization where A of t is t divided by the fourth root of log t. Just reminding you, this classical CLT, you always have the square root. So here you don't have the square root. Here you have something very different from the square root, is regularly varying with index 1. Well, I guess it can never be bigger than t because the function is bounded. So if you divide by something more than t, you always go down to 0. So this is slightly bit less than t because there is the logarithmic factor, right? So there is no clear contradiction, right? There's no obvious objection why this theorem might be false. And in fact, it's true, right? I guess this is a kind of surprising result. And this flow has some other exotic properties.
Sorry, one thing, just this AT does not depend on the function that you...
No, the function, yeah, that's a good point. So the normalizations must not depend on the function, but the constant, of course, here, sigma, can depend on the function.
So when you take an as root n, you mean that the function A should have variance 1?
No, because I allow any sigma here. So I take root n, and then I allow sigma on the right-hand side. Okay? I don't insist on standard normal. Any normal is good enough for me. All right, so this is the first example. I hope you are excited about learning more about this example. So before showing you the construction, let me go a little bit more into ergodic theory. So there is going to be just a list of definition, which I think you all know, but I listed it for reference. Okay, so definitions from your first year ergodic theory class. That you have a probability space, a map which is invertible and preserves the measure. First graduate year.
First year ergodic theory and second year ergodic theory.
Sorry, I meant whatever, like first class in ergodic theory. Yes. Anyways, this is something very basic. So I fix an observable which takes finitely many values. Okay, I denote it by A0, and AN is when I compose it with the map. Ergodicity means that every invariant observable is trivial. It's enough to consider functions that take two values, 0 or 1. But you can take finitely many values. Doesn't make any difference, right? That's the definition of ergodicity. I want to talk about weak mixing a little bit. So probably everyone knows what is mixing, right? So mixing means that the covariance goes to 0. The covariance is the integral of A times Bn minus integral of A times integral of Bn, and Bn is composed with the map. And weak mixing is slightly weaker when you only have the limit in the Chase arrow sense, not in the strong sense. Probably you know what is entropy. Entropy has been discussed earlier today. But I want to focus on the measure theoretic entropy, not the topological entropy, because I have a measure fixed once and for all. Right? So here's the definition. I suppose you have seen it before. So there is the entropy of the partition, and then you look at how at what exponential rate does it grow, and mostly what you care about is whether it is positive or not. Right? So positive entropy systems are somehow very different from zero entropy systems. So that's the distinction, what we mostly care about. Whether entropy is 1 or 2 is less of an interest. One which may be a little bit less known is the K, is short for Kolmogorov, but somehow the story says that Kolmogorov asked not to be called K, not to be called Kolmogorov because he wanted to write papers on it. So he didn't want to put his own name on the paper. But then he didn't write papers. But anyways, it's still called K, but this is short for Kolmogorov. One way of defining it is that you have a non-trivial partition such that this quantity is positive. You might have seen on the definitions, those are equivalent in terms of the triviality of the tail sigma algebra. And last but not least is the Bernoulli. The Bernoulli property is basically what corresponds to IID random variables. So the Bernoulli means there exists an A0 partition, possibly infinite, such that AN are IID and generate the sigma algebra. So this is a bunch of basic definitions in ergodic theory listed in some order of, some sort of order, like stronger properties come near the end of the list, weaker properties come near the beginning of the list, but there is no obvious implication among them. So actually this is one thing that I'm going to focus on which property implies the other one. That's a classical question in ergodic theory. So before getting there, just two more about the CLT I already gave you. So far in these definitions there was no smooth structure, so I'm introducing now the smooth structure. So I have the CLT which I already gave, and then there is polynomial and exponential mixing, which you already saw earlier today, right? Anyways, I'm repeating the definition that you gave. That the covariance decays perhaps exponentially quickly or polynomially quickly. So there is a function on the right-hand side for functions that are, of course, not all observables, but smooth observables. All right. So this is what I've been saying. Which property implies the other one? So the question in general, does property X imply property Y? If so, prove it, or look it up in your textbook. If not, give a counterexample. So an answer to this question is given by the following table. Okay, property X is in the X coordinate, property Y is in the Y coordinate. And if you have a lowercase y, that means yes. So for example, the CLT implies ergodicity. If you see a number, that means the answer is no, and the number specifies a counterexample. Okay, so the first 4x4 minor of this matrix is pretty standard, is available in any ergodic theory textbook. Other examples here down the road are actually getting a little bit more advanced. Maybe one more remark that weak mixing and mixing is combined into one row in this table, and K and Bernoulli is also combined into one row as well as one column, just because it's pretty standard to give an example which is weak mixing but not mixing, and that's the only thing that I hid by colliding these two rows, because otherwise all the other examples and all the other implications are the same. So it's just saving space. And likewise for Kolmogorov and Bernoulli. Actually, I'll come back to it. So example that is Kolmogorov but not Bernoulli is highly non-trivial. That was actually conjectured in ergodic theory for a while to give such an example, but by now is classical, is Kolikov from '82. So it's now classical, but it's far from being easy. But modulo that thing, I collapse these two rows and two columns because all the examples work and all the implications work exactly the same way. So the new result here is the green one. I don't know if green is probably not a good choice for a color. I apologize. So just the green is saying, does CLT imply positive entropy? I don't think this was known before. Well, let me know if I'm wrong, but I'm not aware of previous result. No, the answer is no, because we gave a counterexample. The counterexample is the one that I listed before, because it has zero entropy, and yet it satisfies the central limit theorem. Okay, there are some question marks down the road here. So let me just say a little bit of comment on this one. Exponential mixing implies CLT. That's unknown, but it could be actually quite difficult, because in the framework that we work, I'll try to convince you that CLT is strongly related to multiple exponential mixing. So the question, if I rephrase the question in a way, does exponential mixing imply multiple exponential mixings? Then you might be convinced that this is a difficult question, because this is one of the most fundamental questions in ergodic theory. Does mixing imply multiple mixing? Widely open. So I cannot vouch for this. This might be very difficult, but it's still, as complete a table as it can get. But we are not done here. there is follow-up question. Like you can pick two properties. Do those two imply a third one? And this is why my title is saying flexibility of CRT. So I'm going to fix CRT as my favorite property because I have some background in probability theory and I just can't forget it. So CRT is a favorite one. Fixing CRT and another one, do they imply a third one? Right? So that's a question that you may ask. And that's the next question. Does CRT and X imply Y? If so, prove it. If not, give counterexample. So there are certain pairs of X and Y when the question does not make sense, because if you have a counterexample where for X to Y, then sorry, no, I'm doing it wrongly. So if X implies Y, then putting extra assumption CRT and X will also imply Y, right? So when you see these club signs, that means the question doesn't make sense, or maybe was answered in the previous chart. Okay. So the new questions, here you see actually more new results. So green is new. We have a lot of new examples for flexibility of the central limit theorem. So we have examples for central limit theorem, some property, but not the other one. For example, we can show an example which is K, but not Bernoulli, and satisfies the CRT. Or we have an example which is weakly mixing, but not mixing, and satisfies the CRT. So this is what I call by flexibility of central limit theorem. The central limit theorem can happen without the full-blown picture of chaotic properties, right? So it's kind of a sort of untraditional approach. I don't know if it is untraditional. I mean, it depends on what you call traditional. But there are many examples out there that satisfy all these properties, right? It is great if you can prove that a system is Bernoulli, right? The full-blown chaos, right? It's great. We are all happy. But the question is now partial chaos. Can you have some properties and not the others? Right. Now, I think I'm talking a lot. So yeah, so this is example 7 to 9. So let me tell you a little bit more about the examples. So one I already told you, there is a few more. So theorem 1, for every positive integer m, we can find an analytic diffeomorphism which is mixing at rate n to the minus m, but is not Bernoulli. Furthermore, it is K and satisfies the classical CRT. This is a difficult theorem. So I already mentioned you constructing an example which is K and not Bernoulli is already not easy, is a Kolikov result. And this was actually a question asked by Touvenot for some time, hanging around this question, and now the answer is yes. Of course, the construction goes somewhat similarly to Kolikov examples, so I'm going to explain a little bit the Kolikov construction and what we did on top of that to some extent. So this is probably the hardest theorem, the first one. Okay, and then we have, for completeness, I'm telling you some other results. So the second one is we can do zero entropy with classical CRT. So the example that I brought you before was zero entropy but not classical CRT. So we can do zero entropy classical CRT. The only price that we pay is that it's not analytic. So we can do as high smoothness as you want, but we have to go to very high dimensions. So you give me R, then I'm finding you give me R equals 100, then I find a manifold of 1,000,000 dimensions on which I can find the CR diffeomorphism, which satisfies the classical CRT, but not, I can't do it in the analytic category. Anyways, all results here are not being optimized for in terms of R whatsoever. We are happy if we find one example. Just can you do it in analytic category? I don't know. I cannot. And this one I already said. So you can have weak mixing but not mixing, and you can have polynomial mixing, which is not K and satisfies the classical CRT. So the last two are kind of there for completeness. They have slightly bit simpler proof. I would say the biggest result is the one that I highlighted at the beginning for zero entropy and unusual scaling, and here the first one, the Bernoulli, but not K. Those are the hardest. Okay, so that's about the results. Any questions so far? All right, if no questions, then I'm going to tell you about this class of system, the T-inverse transformations. I'm going to start with the stochastic process, which is also called T-inverse transformation, but in the world of probability theory, it's called random walk and random synergy. So what you're going to do is you have a random walk, and along the trajectory of the random walk, you sum up random variables, but those are frozen. Okay, so you have like, maybe I should try this technology. It works so well, right? So you have like a random walk. Let's say you go here, then you go here, and then you come back. So you've been here like 0 times here, once here, twice here, once here, and 0 times here. And then you just have to there is a random variable associated with each location. So this is, let's say this is the origin here. Oh, I guess not. Cancella. Can I cancella? Okay. Maybe origin is here. So in this example, it would be psi 0 plus twice psi 1 plus psi 2, right? Because I sum these random variables along the orbit. The random variables are frozen. They don't change. It's called random scenery. Okay? So that is the, sorry.
So that's why you call it scenery, not environment?
Yeah, this is not, it's not me, is what is it, standard terminology. The random walk in random environment is when the environment changes the behavior of the random walker. So here the random, it's like a skew product. In dynamical systems terms,
Just my question.
yes, this is a skew product.
Observable.
Huh?
Like a random observable.
No, it's just because it's quenched, you call it scenery rather than annealed. Is that the reason?
I don't think the quenched annealed terminology is quite accurate here because it's not random walk in random environment. So the random walker goes around, he doesn't care about what he sees. It's a skew product. You have a random walk in the base,
Got it. No,
and you get the things in the fiber. So
It's like in a scenery. Okay, understood.
it is a skew product. So classical result is saying that this sum is going to grow like n to the 3/4 in dimension 1. In dimension 2 is almost square root 10, but there is logarithmic correction. And in dimension bigger than or equal than 3 is square root 10. And you have central limit theorem in dimension 2 and 3. Anything bigger than 2, bigger than or equal than 2. In dimension 1, you have a limit, which is not normal, but something else. Okay? So maybe just a tiny bit. So this is result by Kesten, Spitzer, and Bolthausen in this random setup. So maybe just give you a word about why this holds, because this is really the idea that goes into our construction. Sorry. In one dimension, what's going to happen is that these numbers that I have here, 1, 2, and 1, what are these numbers? This is the local time of the random walker, how much time the random walker spends at a given location, right? So these local times are going to basically grow like square root n. You can easily convince yourself that they grow like square root n. And the constant in front is a random constant, which is essentially given by local time of Brownian motion. And now you have a sum of independent random variables, these xi's. Xi's are the independent random variables, but they are weighted with this local time, which is approximately square root n. If it was literally square root n, then what would you do? Well, you take the sum of square root n random variables, the range is square root n, right? So you got like square root n distance, and basically all locations visited like constant times square root n times. So you sum of square root n random variables, of course you get the cubic root of, not cubic, fourth root. You get the fourth root of n, but there is a square root n multiplier in front, so that's how you get the 3/4, right? So the square root of square root n is the fourth root of n, and there is a square root n multiplier in front. And if you do it a little more carefully, not ignoring this constant, then the local time of the Brownian motion will come in. That's a computation, which is, I don't know, I like this computation because it's very transparent, but really the message here is that I have something in the base, I compute local times, and once I have the local time picture, then I sum up something that I observe. In this case, it's just random variables, but as you can imagine, this is a conference in dynamical systems, so random variables will soon be discarded and will be replaced by dynamical systems, right? All right. So what is a T-T-Inverse transformation? Short definition is the same as random walking, random scenery, and that's it, right? Definition is a simple definition. It's the same as before. Long definition is, yeah. So you pick your space to be negative 1, 1, z, and measure is the Bernoulli product measure, and then you have the left shift, and that's the random walk in the language of dynamicist, right? A shift on the product space. And then you have another random walk, which I did like you have this x mu and f, and you have another system which is exactly the same as this one, which I denote by y g nu, And now I'm going to consider the skew product. So the point is I couple them together along this function tau, which is just the 0th coordinate. So I have this sequence of negative 1s and 1s. And if I see 1, then I shift the environment by 1. If I see negative 1, I shift the environment by negative 1. This is what random walk and random scenery means, right? When you're sitting at the table, you want to eat the cake. It's down the table. You don't want to stand up, but you pull the entire table instead of standing up. That's what we are doing here, right? So I'm not letting the random walker go there. I'm shifting the entire infinite line instead. So why am I doing this? Because this is now really looks like a skew product. It is a skew product. You have something in the base x, and then you have something in the fiber which is governed by what is happening in the base. So I write this fancy notation that you have a function capital F, which is a function from x cross y to x cross y, where you apply something in the base, and in the fiber you apply some other function g to a power which depends on x through tau x. Okay, so at this point it's good to stop for a second and tell you for the example of Kolikov. So Kolikov proved.
That was the definition of t times t minus 1.
Yes. Yes, it's crazy. The same object has two different names because two different communities like two different names. Okay, that's it. Random walking, random scenery.
Minus 1, I don't understand.
Yeah, you can apply either t or t inverse.
Oh
That's it. Yeah, I don't like this terminology so much. So, but anyways, this is what they call it. So this is the basic example for a system which is K but not Bernoulli. Okay, Kolikov result 82, and then follow-up result by Dane, Hollander, Stief is that they actually in dimension 1 is K but not Bernoulli, and they considered any dimension. They verified that it's Bernoulli if and only if d is bigger or equal than 3.
So now you're changing the y transformation.
A y transformation, TD transformation.
More states, right? Different functions.
Right, so TT inverse is something we use for traditional reasons, not because we like it. All right, so, yeah, Marco?
Can I give you more terminological trouble?
Yes, please.
This used to be called random walks on orbits of dynamical systems.
I haven't heard this terminology, but I like this one because it's...
in I or something.
Random
Yeah,
walks and
no,
random
but that
scenery
was
is
really
bullshit.
a random walk on the orbit. This instead is a skew product.
Oh, random walk on the orbit is sounds something different.
You can go up and down along this orbit. But Sinai has a couple of papers on that.
I think I have seen stuff like this, but it's different. It sounds different.
Random walk on random scenery is
Why is it not?
Paul Shields' name for the more general result that was proved for objects considered by Calico in his thesis. And Don called
Well,
it
anyways,
TT.
okay, so I apologize if I missed something from the history of related maps. I'm going to give you the definition of the maps that I'm working with. We call it generalized or smooth TT inverse transformation for traditional reasons, but I agree that my terminology might not acknowledge everyone's contribution. So basically, I'm going to repeat the same definition, but now in the smooth category, okay? Because the previous example was not smooth. It was a symbol. It was a symbolic setup, right? So I need a smooth category. So X is going to be, because recall my first slide. I hope you still remember my first slide, like 29 minutes ago. No, wait. It was saying, okay, sorry, I'm not going to repeat it because it's already 29 minutes. So, anyways, I require smooth map. So I need a smooth manifold and a smooth map. And then I have another compact manifold and I have a d parameter flow. Okay, so you can think about d equals 1. I like to think about d equals 1, but sometimes you need higher rank actions. And then you have a smooth map, tau, which couples the two. So it provides this skew product, basically the same definition as before. It's a smooth TT inverse transformation, which preserves the product measure. And symbolic example is the previous one. Continuous, you can imagine, okay? Or is continuous analog. Let me not go into it. After this preparation, it's time to tell you how we construct the very first example, which is let me just remind you, is an analytic flow which satisfies the CLT 0 entropy, and the CLT scaling is t over the 4th root of log t. Okay, so this is the example that I'm going to tell you, and a picture is very similar to, I would say, a dumb version of the pictures that we saw earlier today, because I just don't know how to fold it. So you have a compact for example, a hyperbolic octagon or any compact hyperbolic surface, and you consider the horocycle flow on this compact hyperbolic surface. The way I drew it was not on the compact, so you have to fold. I guess I could do, but so you have to, this is fundamental domain. All the domains are identified, so it's kind of you could fold up this blue circle in the fundamental domain. So this is what I'm going to have in the base, right? Recall, I'm constructing a skew product. I need to tell you something in the base. I need to tell you something in the fiber. Dimension is 1, so no worries about the higher rank actions yet. In the base, you have a horocycle flow on compact hyperbolic surface. Very simple, isn't it? In the fiber, you have even simpler. You can put just the geodesic flow, or actually any NSO flow. So what I have in the fiber, actually in all of the examples, not just this one, in all of the examples, you're going to have very nice chaotic diffeomorphism of flows. You can think about the geodesic flow. So that's what we have in the fiber. And then I just need to tell you tau. So tau would be the how much of the geodesic flow you want to apply in the fiber. And we just pick a winding number in one of the homology classes. Can you hear me? Yeah, one of the homologies. So, for example, how many times you wrap around in this along this direction. It's not quite accurate, right? Because it's an integer number. Tau should be a smooth function, but you can imagine that I am integrating a one form, which is essentially giving this modulo some co-boundary term, which for simplicity I'm ignoring. So I'm pretending it is an integer valued, but it's not because it has to be smooth. Okay?
But I don't understand, because this is just a point, right? So you are integrating t, capital T is just, I don't know. For how long you are integrating? That's not good. You integrate, this given integrated one form, but for how long?
For 0 to t. There is a time t, capital T is time. Oh, sorry, t is, yeah, maybe two things, like the map and time, but yeah, so I integrate. Tau, it's like tau n in discrete. I gave the definitions in discrete time, but now I apply it in continuous time. Okay. But I integrate along like time. Yes. Yes. So I was thinking trying to convince you that t over the fourth root of log t appears, okay? So let's just recall this example that I spent quite some time on, this random walk in random scenery. You want to compute local times, right? How much time you spend in various locations. And then once you understand it well, then you just take a sum in the fiber. Now here, can we do the same thing? If you have a long piece of the horocycle flow, then how much time you spend in various locations? Well, in location in this case is measured by this tau. So how much time you spend at locations where the winding number is 100, for example, a given integer. Yes? So this question is essentially reduced to a, sorry, I forgot to say that zero entropy is an easy exercise because the horocycle flow has zero entropy and the observable has zero mean. So you have Abramov formula which gives you zero entropy for the skew product. Go back, sure. Well, I gave the definition in discrete time, but then I'm using it in continuous time.
So you have a smooth map. That's now a flow. So that's now the
yes, sorry about that. Yes. Okay. Yeah, actually there is a definition downstairs here. So,
okay, so that's
it's a flow. Version. Yeah, that's it's a continuous version. Yes.
And t tau is the integral from 0 to t of the winding number.
Right.
That gives you a continuous.
Right.
But because it's a little strange, no? Because for diffeo it just depends on the point, but for flows it depends on the trajectory.
No, because you applied it like it's like a time bomb map for this guy. So if I spell it out for n, if I spell it out for n, then n will appear in the subscript of the subscript. But I'm not going to write subscript of subscript. And then I did next line. So anyways, yeah. It's just okay. So I'm trying to convince you of this t over fourth root of log n t. Okay. Yeah, I need a little bit. So yeah, this remark, zero entropy. Yeah, we agreed on that. So we want to prove central limit theorem and under the scaling t over fourth root of log t. And we have a tool which is the Björklund-Gorodnik central limit theorem. I should emphasize this is an important tool in our proofs. It shows up in like 2 slides later, but I'm telling you right now. They have a relatively recent paper in which they prove central limit theorem for higher rank actions, which are mixing, exponentially mixing of any order. And they have certain conditions that we need to verify. But basically their setup is very nice for us because we have a measure generated by local times of this whatever system we put on the base. In this particular example, it's a horocycle flow. It's whatever complicated system. It generates a local time landscape. Now this local time landscape gives you a measure, and you can feed it into Bjorklund-Gorodnik CLT. They basically say the measure should be such that, first of all, the measure goes to infinity. Second, there is no much concentration of mass around one area, this second condition. And third condition is that you have to check convergence of second moment. If you have conditions 1, 2, 3, measure goes to infinity, no concentration, convergence of second moments, then you have the CLT. That's what Bjorklund-Gorodnik is saying. There was this discussion earlier, on Monday, I believe, whether we like computing moments or not. So Bjorklund-Gorodnik did the dirty job, because the way they proved their CLT is computing all the moments. And so we can use their machinery and only check the second moment. Okay?
So where's the higher rank?
In this case, there is no higher rank.
So there's no higher rank.
But still, the statement is non-trivial. But Bjorklund-Gorodnik works for higher rank, and for other theorems, we need to put other thing in the base, which is going to be higher rank action in the fiber. But here you don't see it, because this is rank 1.
Wasn't that known before?
For what?
Anyway, as you need it for rank 1, so that's good. That's all what confused me. Yeah.
Yeah, but you still have a non-trivial local time landscape. So you still have a measure, a non-trivial local time landscape, even if it's dimension 1, is not obvious.
Okay.
All right, so I was thinking maybe trying to compute second moment or give you the flavor of the computation for second moment, at least to the point where you see the T over 4th root of log tape popping up, right? So I'm going to go ahead and compute the second moment. So second moment of what? This is the ergodic integral, right? So you get an observable age, which you integrate from 0 to t, composed with this analytic flow that I just defined. I want to explain to you why the second moment grows like t squared over square root of log t. That would be convincing, right? That would be enough because of Bjorklund-Gorodnik CLTs. This is how it should grow. All right, so let's see. Let's go ahead and compute it, right? So I'm computing zeta of ht squared, which is, integral with respect to mu and nu, right? This double integral. Okay, now I'm starting to cheat, okay? First cheating is that I told you geodesic flow in the fiber. Geodesic flow is mixing exponentially, but let me just pretend it's mixing so quickly that actually the correlations are 0 outside of the diagonal, because I'm just ignoring a sum, right, which is convergent anyways. So I'm assuming that this integral is 0 already if n is anything but 0. So it decorrelates right away. Actually, there's two cheatings here. One is that I'm pretending that the exponential decay is already 0. And another cheating that I'm pretending that this function h has integral 0 no matter what is x. Is a function of two variables, x and y. I'm pretending that for every x, the integral of h is 0. Okay? So that's two levels of cheating, but not so serious. All right, so if so, I just, compute the integral of the square of this guy is going to be 4 integrals, 0 to t, mu, nu, right? And one of my favorite subjects is approaching, which is, computing these integrals for a very specific location. It's what is called the local limit theorem. So you have a very specific requirement that you need the winding number to be exactly k. Pretend there's only one integral, okay? Tau of t1 x is equal to k. You require the winding number to be exactly 100, and then you integrate this function. Then what would happen? Now I'm telling you the local limit theorem. Here's the local limit theorem is only one integral from 0 to t, not double. Double makes life harder, of course, but let's say there is only one. Then the local limit theorem is basically saying that this integral, well, you plug in a little bit of Brown. So the Brown part is telling you where you arrive. The major part is that the winding number has to be exactly 100. A minor part is dealing with ages. So I deal with these ages by decomposing the phase space into small squares. And one of these small squares I'm going to denote by a. And on that set, the function of the observable is essentially constant. So I'm just ignoring the observable. The main point is what is written in blue. What is the asymptotic measure of this happening? I claim it's t over square root log t multiplied by the Gaussian density evaluated at whatever value. If that is to be true, then you would get the red right away, because you just sum up a double sum, and this t over square root log t of course, appearing, and then you do the summation, you replace sum by integral. At the end of the day, you get t squared over square root of log t. So I don't know if this is convincing, but to me it seems that basically I reduced the problem to the blue identity, the local limit theorem. Because the local limit theorem, I just use it and plug in and I get it, what I want. So question is, why does the blue / brown, more blue, little bit brown, identity hold, right? Because it's really kind of cheating, no? Because I bring in a formula which already has t over square root log t, and of course I get t over square root log t, but why would this formula hold? And that's where we have to revisit the horocycle flow. I haven't really said anything about the horocycle flow yet. So how do you compute local times for the horocycle flow? That is also called the temporal limit theorem. How do you compute temporal limit theorem for the horocycle flow? Well, if you ask me, I don't want to touch the horocycle flow. It's scary. What I want to touch instead is the geodesic flow, right? And that's a great idea because local, like temporal limit theorem of horocycle flow can be reformulated in terms of standard limit theorem for geodesic flow. That's exactly what we do. This was done at the level of the central limit theorem by Dolgo-Piazza-Rigg, but we need improvement to get this local version. So the idea is very simple. You have a long piece of horocycle here. Okay, I think you cannot read. This is ridiculously small. So you have x here. And then you have long piece of horocycle. And you want to ask what portion of this is spent in the range when the winding number is 100. So what you do instead, you pull this back with the geodesic flow. Recall the geodesic flow is exponentially mixing, so it is sufficient to pull back by log t time. So this is log t. You get a segment, still a horocycle of length 1. Lebesgue measure is being pulled back to Lebesgue measure. This is constant curvature -1. No issues whatsoever. And then you reformulated the question in terms of starting from this piece of manifold, applying the geodesic flow, how likely it is that your winding number will be 100. That's what is called the central limit theorem, or more accurately, the local limit theorem for geodesic flow. And we know that since, I don't know, it's well known in the literature, right? The central limit theorem, I guess, maybe local limit theorem is a little less known, but no surprise. And you see why the log t appears, right? So you apply the central limit theorem or local limit theorem for the geodesic flow for log t time, because that's the time horizon for which you apply the geodesic flow. So that's why square root log t appears in the denominator. Is square root of n is standard scaling. Now n is log t. The t multiplier in the numerator just appears because you had a measure here, which was, Lebesgue measure is t. You pull it back, Lebesgue measure you want to be 1. So you need to rescale by t. So as you get a probability measure upstairs, that's why you get t. And that's pretty much it, right?
So I don't understand. Are you using the fact that the invariant measure for the cycle and the geodesic flow are the same in this case?
Yes, but I don't quite use the invariant measure for the geodesic flow. What I'm using is like a standard pair, because I start with a specific curve, so it's like a singular with respect to the invariant measure, but it's literally an unstable piece. It's a piece of unstable. It's the simplest.
The same, right?
Yes. But strictly speaking, is singular with respect to the invariant measure, but no worries whatsoever, because it's literally a piece of unstable curve. It couldn't be nicer. Of course, it is the foot point, right? Is in the unit tangent bond of the geodesic flow and horocycle flow. I just put the foot points of the vectors. All right. So just one word about the cheatings earlier. So I cheated 2 ways. I'm not going to discuss the one that the other sum, which decays exponentially, that you can handle. You can just take one more sum in front of the big formula that I already had. It was already big enough, so I don't think an extra sum would be any helpful. Another cheating was that, which I said, that I assume that the integral of h is 0 for any x with respect to y. That's a more serious cheating, but that we can take care of by you gave me general observable, zero mean observable. I decompose it into 2. One is the conditional expectation with respect to x that I call h hat, and the other one is when the integral in any fiber is 0. So I gave you the proof for h tilde. I still owe you the proof for h hat. Okay, I gave you the proof of h tilde already. For h hat, I'm just going to use what is available in the literature, and what is available in the literature by result of Flaminio Forni is that this ergodic sum is always grows like t to the alpha over alpha less than 1. So in my scaling, t to the 4th root log n is going to go away. Now, this actually is a pretty deep result, and the limit theorem is a fascinating story. I'm not going to go into that. Maybe you can ask Jens about this, because anyways, as far as I understand, sometimes you get a dense orbit in the space of all bounded random variables. So it's really a fascinating story, but have nothing to do with us, because we push it down, right? Because we have t over 4th root of log t scaling, and it's nothing of this is seen here in this limit.
Can I just ask you
Yes.
one thing? When you said conditional expectation, you meant the marginal. Is that what you meant?
Possibly, yeah.
Okay.
Anyways, it's a
Because
simple.
I'm confused for a second. Looks like you want to take the margin on each fiber, I mean, to make sure that it's zero average for each.
Yeah, I think h tilde is the marginal.
Okay, good. Fine.
Yes.
Because this H would see only the horocycle flow, right? So
H hat only sees the horocycle flow. So I only use results for horocycle flow, which is actually a very deep result and very interesting results. But I kind of lose it in this limit, in the t over 4th root log t limit. I should actually, because no normal distribution shows up in the horocycle flow. And I want normal distribution, so I should get rid of those guys that pop up. It's an interesting story, but it goes to 0. Right, and this I already told you that there is a Bjorklund-Gorodnik CRT, and because of that CRT, we don't have to compute higher moments. But I think this argument would not be that difficult to do for higher moments. You would have, not 2 integrals, but 4 or 6. Odd number should give you 0. But anyways, Bjorklund-Gorodnik did it, so we don't have to do it. All right, so yeah, I think I'm running out of time. So maybe just tell you as a matter of fact that you do need higher order actions for the other results. So some of you may be familiar with these. So standard examples are for ZD actions are Cartan actions, and RD actions are well chamber flows. And for the other theorems, go back to the theorem. Where is it? 1 second. So for the first one, we actually put an Anosov diffeomorphism in the base, an Anosov diffeomorphism in the fiber. Dimension needs to be at least 3. This is actually pretty peculiar because we do have a CRT, despite the fact that you will not have. Sorry. Yeah, you do have CRT in the symbolic setting for dimension 3. The dimension that we use in this example 1 is 3 or bigger. But in the symbolic setting, you would actually have Bernoulli for dimension at least 3. We do not get Bernoulli, so it's a kind of a peculiar property that we managed to find a dimension which is high enough for the CRT to work, but low enough for non-Bernoulli to be violated. The second example goes by just shift on the torus, like translation of the torus. Yeah, I told you already, well, let me repeat. We always put a very nicely mixing thing in the fiber. So the fiber you should always think about is Anosov diffeomorphism or Anosov flow. In the base, in the second example, we put translation of the torus. It couldn't be simpler than that. We put a translation in the torus with a ridiculously high dimension. And the last 2 examples are suspensions over translations. Yeah, I'm afraid I ran out of time, so I'll just go to the end. And yeah, I guess I don't think it makes sense to go into the higher rank actions. And yeah, I think I just wanted to give tribute to this Bjorklund-Gorodnik CRT, which we use left and right. And we have some other work on other applications of the Bjorklund-Gorodnik CRT, but I won't tell you that today because I really ran out of time. So anyways, here's a list of references. And yeah, that's all for today, and thank you for listening.
Thank you for the nice talk. Are there more questions? No more questions. Then we can thank Peter again. We are going to have a break now.